everybody, let's talk about real gases. We've been talking a lot about ideal gases, and I guess we have to ask the question, what makes a gas ideal? Well, what makes a gas ideal is that it follows the ideal gas law. And so the pressure times the volume is actually equal to the moles times the constant times the temperature. If you think about the assumptions that we made in kinetic molecular theory to explain that behavior, there's a couple things that aren't realistic. So we're assuming that the particles occupy negligible space. So a gas is mostly empty space and the particles themselves don't have volume. We know particles actually have volume. So there's a place where real gases probably aren't going to match up perfectly with prediction for ideal gases. Second, we're assuming that particles don't interact, but we know that particles can interact with one another. That's how we get liquids and solids. So there's another place where a real gas might deviate or differ from an ideal gas. So what do we actually see? We actually do see that real gases may not follow ideal gas behavior. If we look at a graph and say we've got 1 mole of a gas, then if we take the pressure and volume and divide that by the gas constant and the temperature, we should get 1 because we only have 1 mole and N is equal to 1. So for an ideal gas, we would expect that PV over RT would always be equal to 1, straight line. If we start looking at real gases, we find that there are some deviations from ideality. And in general, those deviations look kind of like this. What we're seeing here, what I've graphed, is how this ratio changes with a change to the pressure. So as we increase the pressure, what happens to this system? And what we'll find is that initially this ratio decreases, but then at really high pressures it shoots above what would be expected for an ideal gas. So the question is, what's going on and why? So what would cause an initial decrease in pressure? Because for real gases, initially we'll see that our actual pressure is less than we would predict from the ideal gas law. What could be causing a decrease in the pressure? Fewer collisions with the walls. Well, what if those particles were sticking together or were attracting one another when they were close to one another? These attractions are the intermolecular forces you've learned about before. And that means that as the particles are moving past one another, they're attracted to one another, and that's going to slow them down, and that's then going to decrease the force at which they will hit the walls. And so those intermolecular forces will actually decrease the pressure. And it's more noticeable initially as you go to slightly higher pressures, because when the particles are really far apart relative to their size, then they really don't interact much. But as you increase the pressure, those intermolecular forces will start to come into play. But then if you keep increasing the pressure, if we keep increasing the pressure, at some point those particles end up being really close together, really close together. And when those particles start getting really close together, then the space that the particles themselves take up starts to become important. What this means is that under normal conditions, gas particles really are pretty far apart. And so ideal gas equation is a pretty good approximation to everyday life. However, when you start having high pressures, you are going to start to see some deviations where you're going to start seeing initially a lower pressure than you would expect, and then you're going to see a higher pressure as the volume of the particles come into play. And so we see deviations from ideality at higher pressures compared to kind of an everyday standard temperature, or even better, super low pressures. And you have really good agreement with kinetic molecular theory and the ideal gas equation. But at higher pressures, you're going to start seeing these deviations. And that's simply because the particles are closer together. There's another time when you will see deviations from ideality, and that is when the temperature gets very low. If you think about what happens when the temperature gets really low, the particles slow down. So kinetic molecular theory says that average temperature is a measure of kinetic energy, or that temperature is a measure of average kinetic energy. That's better. And so if you decrease the temperature, the particles slow down. Well, if the particles are slowing down, they're going to be moving past one another at a much slower rate. And so those attractive forces are going to have a much larger opportunity to come into play. And so that's another place you're going to see deviations from ideality due to those intermolecular forces. And so your real gases will deviate most from ideal behavior under high pressure and low temperature. They'll be most like ideal behavior at very low pressures and very high temperatures. Standard temperature pressure is kind of in the middle. It's not bad, but it's not going to get you the closest to ideal behavior. Closest to ideal behavior is going to be at very, very low pressure and very, very high temperature, where those particles really can't interact and their volume really is negligible compared to the total amount of space that they're occupying. So you need to be able to explain qualitatively why we would see deviations from ideality. And in class, we're going to work with this idea of if it's intermolecular forces that are going on, how do I then look at a gas and predict between, say, a couple of gases, which one's going to be more different from what would be predicted by the ideal gas law. And so we'll work with intermolecular forces at school. This is the van der Waals equation. So the van der Waals equation takes the ideal gas equation, PV equals nRT, and it addresses these deviations using experimentally determined coefficients, A and B. In this equation, P is your ideal gas pressure that would be predicted. And then we have a term, this AN squared over V squared. This is going to help account for the attractive forces between those particles. And so A, like I said, is an experimentally measured value that can help make that adjustment. And then you'll see in the V term, it's not just V anymore. Now it's V minus NB. And that extra term over here on the right, the NB part, that's going to help account for the number of particles with their size, since we're talking about particles taking up a finite volume. And I've said it 3 times, but I'm going to say it one more time. A and B are experimentally determined, and they're available in tables in your textbook or online. So you can actually predict what the measured value for pressure, volume, whatever, would be for a particular real gas under a particular set of situations or under a particular set of conditions.